Hello. In the previous video, I derived how to calculate a 95% confidence interval for the mean. And we used the sampling distribution and like standardization and then use the standard normal distribution CDF. And that idea can be generalized to any level, any value of confidence level. So I will derive the general formula for a general confidence level. To do that, we are going to set the confidence level at 1 minus alpha. So alpha is the error probability. So your estimator will be correct with probability 1 minus alpha. So alpha can be any number between 0 and 1. So remember, this equation implies confidence level. Confidence level equals to the probability that the true parameter is contained within the interval x bar plus minus the margin. And you have to standardize it. Standardization goes the same. So first, you have to rearrange the probability so that x bar is isolated in the middle term, so that because it's the only random guy, and you are targeting x bar in this analysis. And once you do this step is exactly the same. There is no difference. Subtract the mean, divide by its standard error. So sigma over square root n, standard error, is divided. And as before, mu is cancelled out. Mu cancelled out by this mu. So mu cancelled out during the standardization process. So in the end, you get the same expression for the confidence level. So this part does not change. The only thing changes in this generalization is the number on the other side. So previously it was 95%, but now you have 1 minus alpha instead of 95%. So then now the actual problem is this guy. We now have to find A such that plus minus A contains a probability of 1 minus alpha. Previously it was 95%. So, but we can do the we can use the same rationale to derive A. First, think about this. Between plus minus A, you have 1 minus alpha probability, which means alpha is on the tails. And the probability alpha is split in half for the left and for the right, right? So probability z smaller than minus a is alpha over 2 probability. And so say, like, I'll put it this way. So underestimation probability is alpha over 2. Overestimation probability is alpha over 2, right? So the interval estimation is correct with 1 minus alpha, or it is wrong with alpha probability. Then when it is wrong, it is either underestimation or overestimation. And underestimation and overestimation are equally likely because the normal distribution is symmetric, about 0. So going too small and going too large are equally likely. So in other words, so this means the unknown value A is the top alpha over 2 probability value, right? Previously, it was 2.5% value, and it is denoted as z alpha over 2, z value at alpha over 2. This is very annoying. Like the notation is not consistent with the common objects we use. Like, So anyhow, z alpha over 2 is what we use to denote this value. But actually, even if we use alpha over 2 here, but you have to find 1 minus alpha over 2 from the CDF. When you use the CDF XL, you have to look up probability 1 minus alpha over 2. Then it will give you z alpha over 2 value. And you see in the previous example, we look up for 97.5%. Then that was the cumulative probability. At that probability, you can find the top 2.5% value. And then once you get this value, then it's easy again, because we have to solve this. What we need to do is solve this value from the standard normal distribution and this value from the standardization, match them, equate them, then you get this. So previously, this part is the same, but this part was 1.96. Only this guy changes. And here I used S, which is an estimator for the sigma. So it's the same replacement. And then once you have this margin of error, use this as the margin of error. Add and subtract. And point estimator does not change. So observe this. When you change the confidence level alpha, 1 minus alpha, the only thing affected by this is this guy, z score, z value. So what you multiply to the standard error depends on how much probability you are covering. So if you are covering 99%, you have to extend your interval, so this value must be large. But if you have lower confidence level, the interval does not need to be large. So this number will be small. That's how you change the confidence level by narrowing down or widening the interval. So in sum, to summarize, this is the formula. In the end, even though the derivation looked difficult, very difficult, but actually it was not that difficult if you follow step by step. But anyhow, in the end, this is what you need. Like for when you take the exam, we don't have any more exam, but like for example, like if you had an exam, then you have to memorize this. I don't recommend you to memorize this, but anyhow, well, the long derivation implies a simple result. We have this. So, and it's really nice because you just need 4 things to compute. First, sample average, easy, you know how to do it. Also, calculate the sample standard deviation, easy, you know how to do it. And sample size, even easier. And the z-value, depending on the confidence level. It's a little bit involved, but it's not that difficult. Excel does the work for you. Or also, you may memorize a few numbers that comes in here. So let's think about the effect of each component. When x bar increases, I should have written the formula here. When x bar increases, it only affects the center. So if when x bar changes without changing anything else, then the margin of error is fixed. So the size, the width of the interval does not change, but it's shifting parallel to the left or to the right. When the sample standard deviation increases, which means the data have more noise or uncertainty, so sample standard deviation increases, then the data have more noise. So you need to allow more margin of error. the interval will be wider. So when within the data set, single outcome, the standard deviation of the single outcome varies a lot. If the single outcomes vary a lot within the data, then the standard deviation will be large, and then it makes your analysis more difficult. In the extreme, if this was 0, standard deviation was 0, that means all the observations take one value. That's the mean. So there is no error at all. There is no error at all. So that's an extreme example where your analysis will be always perfect. And when the sample size increases, you have more information, so you can do better. So you can reduce the margin of error, and the interval will be narrowed down, and your interval will be more compact and more informative. And Z alpha over 2 depends on the confidence level. Remember, we learned how to calculate Z alpha over 2, and basically it determines how much probabilities you have to contain. So when you have large number, or you need to cover larger probability, Z value should be larger. These are basic intuitions for them, and these are commonly used confidence levels and the corresponding Z values. So remember, 90%, 95, or 99% are common candidates for confidence level. And for each of them, first you have to think about their error probability. Alpha is 10, 5, 1%, and then divide the error probability on each side, so that you have 5%, 2.5%, 1.5%. And then you have to flip this probability so that the probability is a cumulative probability. Then the other side of 5% is 95, 97.5%, 99.5%. And look up for this value from the standard normal distribution CDF, and then by inverting the CDF, you get these numbers. So these three numbers are very common numbers, and usually, maybe if you have taken another statistics course, now maybe you may have memorized these numbers. Memorizing these numbers, it's not bad. It's actually, so many people memorize these numbers because they are so commonly used. Then in sum, the higher the confidence level is, the larger the Z value is, and the larger margin of error because of this guy, and so the interval is wider. That's a simple relationship between confidence level and its effect. Okay, I'm going to consider another example and I'm going to apply the formula to an example, and which will be very simple. See you in the next video. Bye.